Hello, Chem 2. Here we are again. We're going to try to go through the last of the sections of the gas law chapter. Hopefully this goes better than the last 40 minutes. This video, I taped the entire thing and it didn't save. So we're going to try this one more time. Last time around it took a little over 25 minutes, so it is quite lengthy. You might want to chunk it a little bit, but we're going to go over two concepts. The speed of gas molecules concept, how fast molecules move themselves, and then also how we're going to use what's called Graham's law of diffusion or Graham's law of effusion to look at how fast molecules leave or a container, diffuse a container, and how that is dependent on the molar mass or the size of the gas. Administrative pieces, there are those two owls, the one that is the mastery that you can use to judge your own success. And then there is the required owl, the one that in the event that Carroll County Public Schools gets the opportunity to clarify what we're supposed to do about grades, that's the one that would go into the grade book. So again, there's a lot of misinformation as to what to do about grades during this distance learning concept, but I want to give every one of you the best opportunity to get a decent grade, especially based on all of this craziness. And lastly, as far as administrative items, I've created an exam in the OWL that is going to be available on Friday morning for you to go ahead and take. This will be the last video of the week. So you spend the rest of the time working on the OWLs and working on the test to try to get ready, making sure that you show some degree of mastery. You got 5 attempts at that test. It's an 85-point test. You got 5 attempts at it. Do the best job you can. Again, when Carroll County Public Schools tells us what we're going to be doing as far as grades, I want to give you the best opportunity to have the best grade possible. So there's a test in there that will allow you to do that, especially since we don't have lab reports that were the grade buffers before. Okay, let's move right along with the new information. This chapter is the gases chapter, the gas law chapter, chapter 5. We've covered sections 1 through 5 so far, and now we're going to talk about the kinetic theory. I'll be totally honest, when I taught this class before out of a different textbook, they tended to, and I kind of liked it a little bit better, talk about KMT or kinetic molecular theory at the very beginning, because KMT or kinetic molecular theory is a way to address why the gas molecules do what they do. So some of the concepts that are associated with kinetic molecular theory is as follows. First off, gases, as we know them, are mostly empty space. If you think in terms of a solid or a liquid, solids or liquids, the molecules are in contact with one another, and there's very, very little space in between those molecules. But a gas, they're spread out so much that most of the gas that we see and feel or touch is nothing. It's a big open space where only a very, very tiny amount of the overall volume is the actual molecules of the gas. The gas molecules are also constantly moving in pretty chaotic motion, straight line motion. They go straight until they collide into something else. If they do collide into something else, those collisions are elastic, whether the collision is with another molecule or the collision is with the wall of the container. And then finally, the last piece of KMT is an explanation as to how to conceptualize what gas pressure is. So pretty easy thinking about the 4 variables that are associated with gas laws that we've dealt with so far. Volume is the amount of space, the size of the container the gases are contained in. N, number of molecules, is the number of molecules that are in that container. T is temperature. That's, from a conceptual standpoint, you can think in terms of how fast the molecules are moving, how quickly they're moving in that rapid motion. Technically, temperature is directly proportional to the not necessarily the speed of the molecules, but the kinetic energy of the molecules. And then finally, the 4th variable is in the gas law unit is the concept of pressure. And a way to look at pressure is how often do those molecules collide with the sides of the container. I sometimes will share that a way to think about this, almost all the gas laws could be explained by the idea of freshmen banging into walls. Now, what do I mean by that? One of the things that is kind of true about freshmen, and it's kind of difficult to visualize without, some image here, but think about a room full of freshmen. And those freshmen are in the room, and because freshmen are pretty cool about playing those reindeer games of explaining things, I say, okay, we're all going to walk around this room, and when you bounce into another person, you just bounce off, and you hit the walls, you bounce off, and you just do that. And that would be, you guys are going to be replicating being gas molecules. And most freshmen, if in a freshman class are doing this, they would go through this exercise. So let's say I tell the freshmen, I says, don't you dare move any faster. I'm not going to let any new freshmen in the room. We're going to use just the freshmen that are in the room. And I were to make the freshmen walk around in our classroom, our typical classroom, and say, count the number of times you hit the walls. Then I take those exact same group of freshmen, but I take them down to the auxiliary gym, much, much larger environment. I say, okay, don't walk any faster than you did upstairs, but walk around the gym, but count the number of times you hit the walls. What's going to happen to the number of times they're going to hit the walls? Well, hopefully, it's pretty common sense that they're going to hit the walls less frequently. What that means is, and we saw this with Boyle's law, as you increase the volume of the gas, the pressure of the gas is going to decrease as long as you keep the temperature and the number of molecules the same. That was Boyle's law. A way to explain or way to conceptualize the pressure is the number of times that the molecules are colliding into the walls. So I use that image occasionally of just thinking in terms of these molecules, these people walking around, make them move faster, they're going to hit the walls more frequently. That means if I increase the temperature, the pressure is going to go up. That's going to be Keeler-Sachs law. All the laws can be kind of explained using this concept of the molecules bouncing around and bouncing into the walls as a container, and that would be the pressure. So here they are in this rapid straight line motion. But one thing I want to make sure this is clear is we're not talking about per se the actual speed of the molecules. We're talking about the average speed of the molecules. What I mean by that is at some temperature, the molecules are not all going to be moving at the exact same speed, but they are going to have an average speed that is going to be directly proportional to the square root of the temperature. Let's look at this. So this is a graph that shows what's called the Boltzmann distribution of molecules. And this applies to everything, but it applies probably most clearly to gas molecules. This represents, the red picture represents an oxygen container. Has some container, it's at 25 degrees Celsius, and in that container, I have molecules that are moving at a bunch of different speeds. Some are much slower, some are much faster, but on average, they're running at about, little over 400 meters per second. What this means is that the average speed is 400 meters per second, but that does not necessarily mean every single molecule in that gas is going to be moving at the same 400 meters per second. They're distributed in such a way that some are slower, some are faster, but most of them are in the bulk of the area very close to the 400 meters per second. Whereas if I already increased the temperature to 1000 degrees Celsius, then there would be the average speed would be somewhere in, I guess looking at this graph, somewhere around 800 meters per second. So double the speed at going from 25 to 1000 degrees Celsius. I have increased the temperature dramatically, so therefore I'm also going to increase the number of molecules that are moving faster, but again, some of the molecules are still moving this slow speed, but a lot more of the molecules are moving at this greater speeds way out here. So as they say here, at 1000 degrees, there's a lot more molecules moving at 1600 than there are in the 25 degrees, so which means it looks like there's almost none of the molecules are moving at 1600 meters per second. Again, there's a distribution, and we're going to focus on this idea of the average speed, not necessarily the absolute speed. So how do we calculate the average speed of the gas molecules? Well, the variable we use is U, NU is the root mean square speed. Sometimes it's referred to as RMS. The root mean square speed is calculated by taking 3 times R, and we'll talk about what R to use in a second, times the temperature in Kelvin. We always use the temperature in Kelvin, divided by the molar mass, and then take the square root of that. Now, molar mass, as we know it, is in the units of grams per mole. R, as we used before, 8.314, is in the units of joules per mole degree Kelvin. So what you're going to see in a second is we can't use 8.314, we have to use a different R value to try to make sure we compare to the grams for molar mass. But let's conceptually look at what this means. Speed of the molecules is dependent on 2 things, 2 very, very large things. One is the temperature. Since the temperature is in the numerator, if I increase the temperature, I'm going to increase the speed of the molecules. Now, I'm not going to increase it proportionally. We saw that in the last example, going from 25 Celsius to 1000 Celsius. It doubled the temperature, but it is going to increase by a factor of the square root of the change. So that speed the molecules are going to move is going to increase by a factor of the square root of the change in the temperature. But it is going to be in the direct direction. Temperature goes up, speed of the molecules is also going to go up. Vice versa, on the molar mass, since it's in the denominator, since it's in the bottom, it's going to, if you increase the molar mass, the speed is going to go down. Think from a mathematical standpoint, 1/2 is greater than 1/4. So as you increase the denominator, the number is going to get smaller. As you increase the denominator, the number is going to get smaller. But again, it's going to increase by a factor of 1/2, factor of the square root of the molar mass. I always use the visual image of take say me and let's say either Ella from Mod 4, or who do we have in Mod 3 that is very, very tiny? I don't know. Still, again, I did this with the last video. Couldn't come up with somebody in 3rd mod. Should have looked up, try to figure who I would use as an example. But suppose we take myself and another student, and we put them into 2 wagons. Me in one wagon, and one of you guys in another wagon. One of our smaller students. We push the 2 wagons with the same exact force. Well, the one that has me in it, because it's has more mass, is going to not move as fast as the one that has a smaller person in it. So as I increase the size of the molecules, I'm going to decrease the speed at which the molecules move. So they are proportional, but they are inversely proportional. And the inverse proportionality is also to the square root of the molar mass, not just directly to the molar mass. This is an interesting image of an experiment that gets done occasionally, and it's one where they react hydrochloric acid, HCl, actually use HCl on a cotton swab or something on the bottom, and then can react it with ammonia, NH3. And the 2 gases, if you think in terms of this, you put a little puddle of hydrochloric acid in one, a little puddle of ammonia in the other one, of these 2 little cups. And what's going to happen is they both are going to fume. They're going to form, the gas molecules are going to escape the very, very concentrated acid and very, very concentrated ammonia. And when ammonia reacts with hydrochloric acid, you make a compound called ammonium chloride, which is a solid. And you see right here that there's this band that forms in the tube as the molecules in the one tube come up and they meet the molecules in the other half of the tube, and they connect in the middle and form this nice little band. Now the band is not in the middle. That's because the slower molecules are going to be on this side, on the right-hand side, because they're going to go a lesser distance in the same amount of time as the smaller molecules on this side. Well, let's think about which molecule is which. HCl, Cl has a molar mass of around 35, plus 1 for the H, that's 36. As opposed to ammonia, ammonia is NH3, nitrogen has a atomic mass of 14 plus 3 hydrogen, so it's 17. Hydrochloric acid has a molar mass of 36, and ammonia has a molar mass of 17. Ammonia is smaller. So ammonia would be on the left-hand side, and hydrochloric acid would be on the right-hand side, because the ammonia gas would go a further distance in the same amount of time because it's smaller as compared to the larger molecule. And therefore, we can figure out which one's which of the two by doing that, but it would definitely be different. You could also do it the other way around. We could actually find the distance that was traveled and compare the two and get the relative molar masses of the two compounds. Let's see how an application of this particular law. So I want to calculate what is the average speed, the root mean squared speed of nitrogen at 25 degrees Celsius. Well, things we know, temperatures at 25 degrees Celsius, which we know we have to change to kelvins. We know our R. Now, again, I said that for this particular application, we would use the R of 8.304 joules per mole Kelvin. But depending on whether or not you remember this from conceptual physics or not, a joule is a kilogram times meter squared over second squared, which means we're going to have the unit of the kilogram as our mass unit. We know our molar mass is going to be in the units of grams per mole, so we need to make sure our R is in the units of grams per mole. So the grams is where we get the times 1,000 to our value. So we got 8,314 grams times meters per second squared, mole squared, and kelvins. Complication, we just have to use a different number because of this. And then it asks for the average speed of the nitrogen. So we're going to plug those numbers in. This is our equation. R, we already know what we're going to use. T, we're going to use the Kelvin temperature. Molar mass, we're going to use our molar mass. And voila, when you put it in, 3 times 8,314 times 298 divided by 28 grams per mole. You do that math and then take the square root of that number you get that the average speed of the gas molecules at 25 degrees Celsius, if you're talking about nitrogen, is going to be 515 meters per second. Again, that's the average speed, not the actual speed. That's the average speed of the molecules, not the actual speed. That just means most of them are in that speed. Okay, now let's look at the other law that's associated with this particular section, and it's called Graham's Law of Diffusion, also seen as Graham's Law of Effusion. Your book actually deals with the effusion part. So what is diffusion and what is effusion? Well, diffusion is the fact that whenever you've probably heard of things called diffusers, where there'll be some container that warms up some oils or some fragrance and spreads good smells throughout a room to make the room smell better. Those things work by allowing the gas molecules that are there to be agitated, and then the gas molecules spread throughout the room. That process of the molecules spreading throughout the room is called diffusion. Let's go back to our freshman mentality. If I take all my freshmen and say, okay, we're going to do this experiment, but you guys all start in that corner over there, but move in completely and utterly random directions, bouncing off of walls as you see fit, over time, those freshmen are going to spread out throughout the entire room. They're not going to just congregate in the corner, and they're going to bounce around randomly and spread throughout the room. Also, we should know that some molecules are going to move faster than others. Big molecules, we already said, are going to move slower than little molecules. There's an analogy that I always use, or an example that I always use, of suppose one of our students happened to have some breakfast burrito, something where they went to Taco Bell and decided to get a breakfast burrito with all the beans and all the fixings, and well, they got a little bit of flatulence going on. They got to let loose with some stinky gas. Well, one of the things that they might try to do, which is kind of interesting, they might try to cover it up. So maybe they just say, wait a second, as soon as I let loose here, I'll just go ahead and spray my Axe spray, or I'll spray my perfume, and no one will be the wiser because they'll smell the perfume. They won't smell the stinky smell of the bean burrito. Well, the reality is that won't work, because the flatulence molecules are using methane gas or something like that, and they're very, very small, and they will move faster than the perfume molecules, which are usually a little bit larger. They're usually esters of some sort, and they have that smell. The molecules are a little larger. So if they were to spray at the exact same time as they let loose, quote unquote, the people close by would not notice anything, but people on the halfway to this other side of the room or to the other side of the room would smell this really rancid smell. And then after that would come this wave of whatever the fragrance is. They would come at different times based on the size of the molecules. First time around when doing this video, my wife had made the comment that I guess the moral of the lesson is to go ahead and basically make sure that you spray before you fart. That's kind of not what I was going for, but you know, it's true. Just cover up the whole room with the smell before something else comes flying out. Anyway, that is your life lesson. That's diffusion, where the gas molecules will spread into the entire container. It's pretty slow. Now, effusion is one where you can do a little bit of analysis. If you take a container and say you allow that container that has gas in it, you put a small pinhole in that container, the gas molecules will leak out, but they'll leak out based on how quickly they find the hole in the container. The molecules that are going faster will bounce, and will find the hole in the container quicker and more often than the molecules that are moving slower. So there is a mathematical relationship, again, to the speed at which the molecules move and the speed of effusion or speed of diffusion. So the rate at which the molecules leave the container is based on two things. One's the pressure of the gases, how much pressure they're under and how many molecules are banging into the walls to begin with, and then how fast the molecules are moving. Let's think about it. Go back to the freshmen banging into walls. If the freshmen are in a room and I make them walk around and bounce into walls, and then I open the door, and if they happen to randomly hit where the door is, they get to leave. Well, the faster the molecules are moving, the more often they're actually moving, the more often they're hitting the walls, the more likely it is they're going to find the door and be able to escape. Also, the faster they're moving, the more often they're going to hit the walls, and the more likely it is they're going to find their way out. So the effusion of the gases is based on those two factors. Mathematically, okay, here's the mathematical Graham's law of effusion. Mathematical relationship between the two is the rate at which the effusion takes place of one molecule as it compares to the other molecule. It's a ratio, is equal to the inverse. Okay, notice that in this situation, B is on top, A is on the bottom, and over here, A is on top, B is on the bottom. The inverse of the molar masses raised to the square 1/2 power, or taking the square root. What that means is big molecules will effuse faster. Big molecules will effuse slower than little molecules, but not directly proportional to their size. Proportional to the difference in or the ratio of the square root of their sizes. Let's look at an application here. So here's an example of a visual to show the two gases, big molecule, little molecule. Big molecules, when allowed to escape, less will escape relative to little molecule. Okay, it just means they're moving faster. So they're moving faster, they're going to be more likely to find that hole. So here's the experiment. In an effusion experiment, what they do is they take the same concept and they put into one side, they'll put a gas and open it up, and put it in another container, put a gas and open it up. In both situations, the flask is allowed to open up, and it's going to take, for argon gas, it's going to take 32 seconds for the gas to get up to 12.5 millimeters of mercury. Okay, so what that means is, and I don't know which one is which here, so we'll get to this in a second. It takes 12.5 seconds for the pressure in this container at the bottom to get up to 12.5 millimeters of mercury. I take another gas in another container, exact same size, exact same temperature, exact same pressure, and this time around, I allow the gas to build up that 12.5 millimeters of mercury, but now it takes 48 seconds. And we're going to use that information to calculate the molar mass of the second compound. Well, let's think about it. Is the new compound going to be bigger, or is the new compound going to be smaller than the argon? Argon took 32 seconds to get up to 12.5 millimeters of mercury. The new compound, X, took 48 seconds. It took longer for it to get up to the 12.5. Since it took longer to get up to 12.5, that means it took longer for the molecules to leave the container. Therefore, hopefully you realize that the gas, new molar mass, should be greater than argon's molar mass. Okay, does that make sense? It took longer. So since it took longer, 48 seconds compared to 32, since it took longer, therefore, to get to the same pressure at the same temperature, since it took longer, means that the molecules were moving slower, which means they were larger. So how would we mathematically figure this out? Well, things that we're given. We are given the information about the volume. We're given the pressure that both flasks are going to get to. We're given the time that each gas takes. We are told that the temperature is the same for both sides. We saw a measurement that the pressure is the same for both sides, and we see that the volume is the same for both sides, so that's kind of implied. We can calculate the rate of effusion. I'll talk about that in the next slide. We know the molar mass of argon. We looked that up off the periodic table, and it's asked for the molar mass of X. So here's the process. Since we know temperature, pressure, and volume are the same, that tells us that the number of molecules is the same. Pressure, temperature, and volume are the same, therefore the number of molecules is the same. PV equals nRT. If P is the same and T is the same and V is the same, then the number of molecules is going to be the same also. What that means here for effusion, because if effusion is this ratio of how many molecules leave in an amount of time, how many molecules leave in an amount of time, then N is going to be the same for both of them. You're going to divide it by whatever amount of time it took for that effusion to take place. So we're going to plug them into Graham's law, rate B over rate A, molar mass A over molar mass B. There should be a 1/2 there. I have no idea why that's not there. And then I put in argon and X into the equation, and then I'm ready to plug some numbers in. So my rate of X is N over 48. My rate of argon is N over 32. I don't care what N is. I could calculate it if I wanted to, if I were given the actual pressure, the actual volume, and the actual temperature. That seems to be not necessary, but we'll just use this N saying it's the same thing. Molar mass of X. Now, that's the rate of argon, rate of X, molar mass of X, molar mass of argon, and then we need to do our math. So this, since n's cancel, we get 48 divided by 32, that's 1.5 is that equation. Then in order to get rid of the square root, we're going to square both sides. So 1.5 squared is equal to all of that squared. So 2.25 is 1.5 squared. Molar mass of X over 39. And then in order to get molar mass of X by itself, we're going to multiply these two numbers together. And we get that the molar mass of our X gas is 89.9 grams per mole. Like we said, it should be larger. Argon is 40. The new gas is almost 90. Anyway, so that's the end of this chapter. Hopefully, this new distance learning process is not too painful. We do the best we can with the situation we're in. So what's next? First off, you have an assessment to take. Actually, first off, you have practice problems to do. You have your OWL required problems to do. Hopefully, you've been plugging away at those. I'm going to check online in a second to see how that's going. And then you have your gas law assessment to take. You have 5 attempts at that to get the best grades you can. Please take care of that as quickly as possible while the information is fresh in your mind. Use the OWLs to help you. The questions are very, very similar on the assessment. These are not questions that I created. These are questions that were created by the OWL. And then what we'll do starting next week on Monday, we will do the thermochemistry chapter. I think it's chapter 8. We'll do that one on next week, where we'll start incorporating where the heat is involved in a chemical reaction. So far, we talked about how fast they've gone, how how much of gases and how much of solids are made and all that fun stuff, all the stoichiometry stuff. Now we're going to talk about how much heat is made and how to determine those values. Look forward to seeing some of you guys maybe this afternoon, where we have our first flex meeting from 2 o'clock until 3 via the Microsoft Teams platform. It is optional. You do not have to come to those, but we're going to use it as like kind of a flex where you'll be allowed to ask questions as you deem necessary. Utilize your teammates and utilize me to give some kind of feedback to help out. So anyway, I look forward to seeing you guys again. Stay healthy, stay safe. Hopefully this someday before this craziness is over, not too soon, too far away, I actually get to see you guys again. But always remember, never forget, sig figs do matter. You guys have a great day. I will see you maybe this afternoon.